gave a theory which is named as Dalton's theory of atom or Dalton's atomic theory, right? In which he just tell that the atom is indivisible particle, right? We can't divide atom in subatomic particles, right? So first Dalton in 1808 he gave a theory which is known as Dalton's atomic theory, right? We will see these in details. After that, in 1897, J.J. Thomson, he came and he performed a certain experiment which is known as cathode ray experiment. By this experiment, he discovered electron, right? And he proved the Dalton's atomic theory wrong, right? Because Dalton, what he said that atoms are indivisible, right? But after the discovery of electron, his theory proved wrong because we can atoms has also a subatomic particles which is known as electron after this discovery, right? After the electron discovery. After that, in 1911, Rutherford performed an experiment which is known as Rutherford gold foil experiment, or it is also known as alpha particle scattering experiment. Rutherford alpha scattering experiment. Right,
Okay.
right. Yeah. After that, the Bohr model of an atom came. Right, Bohr gave an atom in which uh, he just gave the he just tell us about the details information about the energy levels of electron, right? And at that time, this model was very popular, right? But after some time, ये model भी fail हो गया, right? After some time, this model also become fail. And after that, quantum mechanical model of an atom came, right? Which is a very important model of an atom, right? But आपने ninth class में Dalton's atomic theory you have read, J.J. Thomson you have read, right? But in this chapter, we will mainly focus on these two, Bohr model of an atom and quantum mechanical model of an atom. Clear?
Yes, ma'am. Yes, ma'am.
Okay, so I'm starting with Dalton's atomic theory.
Okay.
Okay, so see. So there are some postulates which given by Daltons. Okay, there are five postulates which is given by Dalton. So let's see one by one. So he said that all matter is made up of tiny indivisible particle which is known as atom, right? He said that every matter consists of a very tiny particles which is indivisible, right? And he termed it as an atom. Okay. Second, second postulate of Dalton's theory was that all atoms of specific elements are identical in mass, right? He said that all the atoms of specific elements are identical in mass, right? Size and other properties, right? But but he didn't explain the isotope, isotope, राइट उन्होंने
Yeah.
आइसोटोप के बारे में नहीं कहा था राइट बिकॉज वी नो दैट व्हाट आर आइसोटोप्स हैव सेम atomic number but they have different atomic mass, right? Isotope are of same elements के isotopes होते हैं but they have different mass. But he said that all atoms of specific elements are identical in mass, right? But which is wrong, right? Further, when because he didn't explain about the isotopes. Isotopes also exist, which have different atomic mass, right? Which have different mass number, right? And they are
Yeah.
for of yeah, for example, carbon isotope. Atomic number is same, but the mass number, for example, 12 and 14. Okay, this is the isotope of carbon. So here you can see that these are of same element. These are of same carbon element, right? But they have different mass number 12 and 14, right? They also exist in nature, right? So Dalton's doesn't give the information about the isotope. Clear, Sanidhi?
Yes, ma'am.
Yeah. And yeah, he also said that atoms of different elements exhibit different properties and vary in mass and size. He said that different elements. Sorry, just a second. Hmm, yeah. He said that different elements exhibit different properties and vary in mass. He said that different elements have different masses, right? Different masses, but
Yeah.
and sizes, but he doesn't account for the isobars. What is isobars, Anidhi? Isobars have same mass number but different atomic number,
Okay.
right? Isobar are different atomic number but same mass number. Okay, so that's known as isobar. So he doesn't give the information about the isobars. Isobar also exists, and isobar are of different elements का isobar exists करते हैं, right? But they have different atomic number, right? Isobars have different atomic number, but atomic mass is same. Third postulate of Dalton's atomic theory was that he said that atoms can neither be created nor be destroyed, right? It was
Yes.
okay. It was right. This postulate was right. Atoms can neither be created nor be destroyed, right? He just explained the law of conservation of mass, right? He just gave the account for law of conservation of mass. What was
Mm,
law of conservation of mass? Mass can neither be created nor be destroyed. Only it can transfer from one form to another. Right?
another.
Yeah. Fourth postulate of Dalton's theory was that atoms of different elements combine with each other in a fixed simple whole number ratio. Right? He said that atoms combine in a simple whole number ratio, fixed simple whole number ratio. Right? But you can see there are some elements. So see, he said that different elements can combine with each other in a fixed simple whole number ratio, like carbon dioxide, like N2O, nitrous oxide. So here you can see the carbon is 1, right, and oxygen is 2. So the ratio will be 1 is to 2, right? Nitrogen is 2 and oxygen is 1, right? So the ratio will be 2 is to 1. These are simple whole number ratio, right? So it is right. But there are some complex organic molecules which do not combine in a simple whole number ratio. For example, glucose, C6H12O6, right? So these are not simple whole number ratio. These can't combine in a fixed simple whole number ratio, right? These are not simple whole number, right? For example, in a case of sucrose, C11H22O11, right? ये भी क्या आपका large number है. This is not a simple whole number ratio, right? So atoms need, it is not necessary for atoms of element to combine in a fixed simple whole number ratio, right? There are some exceptional case like complex organic molecules in which they did not combine in a simple whole number ratio. Clear, Sanidhi?
Yes. Yes, ma'am.
Okay. Is there any doubt you can ask in between? Okay.
Okay, ma'am.
No need to hesitate. Fifth point was that he said atoms can be rearranged, combined, or separated in a chemical reaction, right? He said that atoms, for example, if any chemical reaction is during a chemical reaction, what happens? Some atoms rearrange, right? They rearrange to form the product. Sometimes they together, combine with different atoms to give the product. Sometimes they separated, right, to give the product. So this point was right. This postulate was right because in a chemical reaction, atoms can be rearranged. Sometimes they combined or sometimes they separated, right, during a chemical reaction. So this postulate was right. Okay. So all the postulates, there are five postulates. So each and every postulate is clear. Is there any doubt in
Yes,
any
ma'am.
point?
No, ma'am.
Okay. Okay. So just write it down.
Okay.
First, try to first try to understand the concept and then make the notes along according to you. Okay, you can make short notes also. जैसे आपको समझ में आता है, you can make notes.
Okay, ma'am.
Just write it down and update me. Done, Sanidhi?
Ma'am, 1 second.
Okay.
So, ma'am, isobar means
Atomic mass is same, but the atomic number is different.
mass is same, but
Number is different. Atomic number is
okay.
different.
Yes, ma'am, done.
Okay, so let's see that what are the limitations, what are the drawbacks of Dalton's theory. Okay. So see, first drawback is that it doesn't account for the subatomic particles because he just said that atoms are indivisible particles, right? उन्होंने subatomic particles की बात नहीं कही थी. So that's the main limitation, right? So he doesn't give the information about the subatomic particles because atoms can also be divided into its subatomic particles, which was further explained by the J.J. Thomson, right? Which was further proved by J.J. Thomson using the experiment cathode ray experiment. Right?
Yes, ma'am.
Second point was that it doesn't account for isotopes. It doesn't tell the information about the isotopes, right? Third was that it doesn't account for isobar, as I explained it to you. See, the examples of isobar, you can write it over here. Argon and calcium, right? So
So,
you
ma'am,
can see,
here the mass number is different,
no, if the
but
mass number is same, mass number is same, bache. Mass number we write in on the superscript.
oh,
40 is
okay.
the mass number, but the atomic number is different,
Okay, atomic
right?
number. Okay.
So here in the case of argon and calcium, you can see the mass number is 40, but the atomic number is 18 and 20. So these are isobars. So sorry, yeah, atomic mass is same. Yeah, these are isobars. Yeah. And what is the isotopes? For example, isotopes of hydrogen exists in three isotopic form. This is protium. When the atomic number and mass number is one, then it is protium. When the atomic when the mass number is two, it is deuterium. And when the mass number is three, it is known as tritium. So here you can see that atomic number is same for all these, but the mass number varies, right? One, two, three. So it is the isotope of hydrogen.
Okay.
Third, third drawback of Dalton's theory was that he said that elements can combine in a fixed simple whole number ratio. But as I told you, that elements, it is not necessary for elements to combine in a simple whole number ratio. Right. For example, in the case of complex molecules like glucose and your sucrose, glucose, etc. So these do not combine in a simple whole number ratio. Okay, so this was the drawback. Fifth drawback was that he doesn't explain about the allotropes. He doesn't tell that the differences in the properties of allotropes. See, for example, carbon. Carbon existing. Carbon has two allotropic form. Now, first tell me, Sanidhi, what is allotropes? Do you know what is allotropes? What are allotropes? See, allotropes are of same element के होते हैं, but they have different chemical and physical properties, right? Allotropes are of same elements, but they have different chemical and physical properties.
Okay.
If you want to write, you can write down. For
Yes, ma'am.
example, carbon has two allotropic forms, graphite and diamond, right? And you can see that graphite and diamond has different chemical and physical properties, right? So these are allotropes of carbon. Both consist of carbon, both are made from carbon, right? But they have different physical and chemical properties. That's why they are known as allotropes. And Daltons failed to explain about the allotropes. Why there is a difference between the physical and chemical properties of allotropes, right? Both contains only carbon, but why there is a difference between physical and chemical properties? Dalton's doesn't explain that, right? He failed to explain that. So that's the demerit of this Dalton's theory.
Okay.
Write it down. Have you written?
No, ma'am.
Okay, just write it down. After the Dalton's theory, various discovery happened, right? The discovery of various subatomic particles like protons, electrons, your neutrons, right? And many other like X-rays, etc. So during the 19th century, yeah, it was happened in 19th century. It leads to the idea that the atom was no longer indivisible, right? Atoms is no longer indivisible, and they have a smallest particle also, right? They are the smallest particle and they contain subatomic particles also. Okay, so this after the discovery of subatomic particles, this Dalton's atomic theory failed, right? These become wrong.
Oh. Allotropes are they belong to the same element but have different chemical and physical properties, right?
Yes, yes.
Okay, ma'am. Done.
You can write down the examples of allotrope like carbon, graphite, and diamond.
Yes, ma'am. Done.
Okay. Now let's see the discovery of fundamental particles. Okay, so atoms consist of several subatomic particles, right? Like neutron, proton, electron. Yeah, and there are much more fundamental particles. Like there are much more subatomic particles, you can say. Subatomic particles are very neutrino also, positron, etc. Like, but out of these particles, electron, proton, and neutrons are fundamental particles, right? And what are fundamental particles? Fundamental particles are those particles which cannot be derived from the other particles, right? Those are
Yes.
known as fundamental particles. And there are several subatomic particles like electron, proton, neutron, other than these neutrino, positrino, etc, right? But out of these, all these, there are only three subatomic particles, fundamental particles, which is known as electron, proton, and neutron. Clear? Fundamental
Yes,
subatomic
ma'am.
particles are only these three, right? But if someone asks you the subatomic particles, so there are other than this इलेक्ट्रॉन प्रोटॉन एंड न्यूट्रॉन के अलावा भी और भी सबatomic particles होते हैं, right? Like neutrino, positrino, etc. But these three are fundamental subatomic particles. Clear? So first, one by one, we will see the discovery. So first, we will see the discovery of electron. How the electron discovered. So electron was discovered in 1897, right, by J.J. Thomson, right? And electron is negatively charged particle, right? Electron is negatively charged particle. So let's see what he did, how he performed the experiment. So he just take a, see, this is a, I'm just zooming. Okay, he just take a glass containing, this is the glass chamber, right? Glass chamber, which is known as cathode ray discharge tube, right? This chamber is known as cathode ray discharge tube, right? And this is a cathode tube which is made of glass containing. Here you can see there are two metals, right? Here you can see there are two metals. Just a second. Nice. Hmm. So what is this? This is a cathode ray discharge tube, whole setup, and this is your. These are two electrodes. These are two electrodes. Okay, two metal pieces of of metals, which is known as electrodes. This is cathode, which is negatively charged, and here this is anode. Okay, cathode is what? Cathode is negative charge, and anode is positive charge. Okay, just remember that. And what he did, and this is there's a condition for this experiment. J.J. Thomson uh, had done this experiment on this condition. They just take the low pressure and very high voltage. Okay. At this condition, electrical discharge through the gases could be observed. Okay. At this condition, electrical discharge through the gases can be observed. So he just take the low pressure and very high voltage. Okay. So here you can see that here is a vacuum pump. Okay, so from here he just partially evacuate this gas chamber, this cathode ray discharge tube, right? Because here are some particles, gas particles there inside the this discharge tube, right? So he just partially evacuate this discharge tube using this vacuum pump. Okay, and again, I'm just explaining it. What he did, this is a discharge tube. Here, these are two electrodes over there, cathode here, and here is negative. Here's a negative electrode, which is known as anode. Okay. Now from here, he just adjusted the different gases pressure by evacuation of glass tube, right? And what he did, when a high voltage, right, from here you can see this is a energy source, battery source. So when he apply a high voltage, which is approx 10,000 volt, right, 10,000 volt is very high voltage. So when very high voltage is applied across these two electrodes, what happens? The current starts to flow, right? The current starts to flow, and the beam of particles in the tube can be observed. Beam of particles from the tube from the negative electrodes to the positive one, right? Negative electrodes to the positive one, positive, right? So when high voltage is applied, what happens? The particles, the radiations move from the negative electrode, which is cathode, towards the positive one, right? And these rays were called the cathode ray. What are these rays called? These rays were called the cathode ray or cathode ray particles. Okay, now see, but J.J. Thomson, these cathode ray was invisible particles, right? Cathode ray was invisible particles. So how J.J. Thomson can observe it from his naked eye, right? So for that, what he did, he just perforate this anode. Perforate means he just make little holes in the anode, right? And he just he just coated this glass wall by zinc sulfide. Why only zinc sulfide? Because zinc sulfide, or he can also use the any fluorescent material, fluorescent, or you can say phosphorescence. Now here comes a question, what is fluorescence material or phosphorescence material? So these are some chemicals. Phosphorescent is a ability of certain chemicals to give off visible light, right? After absorbing radiation, right? For example, if some radiation is not visible through our naked eyes, like UV, right? UV is not visible from our naked eye. So this fluorescent material, when this rays, when it strikes on this material, fluorescent material, zinc sulfide, here you will observe some bright spot, right? Some luminous spot will be observed on this zinc sulfide material, right? That's why he used the zinc sulfide material over here, right? He just coated this zinc sulfide material on this glass wall behind this anode, behind this perforated anode, right? Clear or not, Sanidhi? What he did?
Yes, ma'am, I'm clear.
Okay. So what happens? This flow of current from the cathode was further checked by making hole in the anode, right? Hole in the anode, which means perforated anode. And he just coated the behind of this anode with phosphorescent material, which is zinc sulfide, right? Now, what he observed that when these rays, when these rays are coming, when these rays came, right, after passing through this anode, this perforated anode, because there is a hole in this anode, so it will pass this anode and it will strike on this zinc sulfide coating, right? So when these rays, after passing through the anode, strike the zinc sulfide coating, a bright color spot is developed on the coating, right? A bright color spot will develop on the coating. Okay, that's the observation of J.J. Thomson. He observed a bright color spotting on the zinc sulfide material. Clear or not?
Yes,
Everything is
ma'am.
clear. What he did, all the setup, all the procedure, what he did, step by step.
Yes, ma'am.
Okay. Now see what are the conclusions of this experiment, right? What are the observations and what are the conclusions? So cathode ray, he just observed that, J.J. Thomson observed that cathode ray start flowing from the cathode and move towards the anode. Okay, cathode ray कहाँ से flow हो रहा था? It was flowing from the cathode towards the anode, right? So because cathode is negative, right? Cathode is negative and anode is positive. So, and we know that opposite charge attract each other, right? Opposite charge attract each other. So we can, J.J. Thomson, he just conclude that this cathode ray is negatively charged particle. Why negatively charged particles? Because it was coming from the cathode ray and it was going towards the anode, right? Because anode is positively charged, so cathode ray must be negative charge. That's why it is attracting towards the anode, right? It is attracting towards the anode electron because it is a positively charged, sorry, negatively charged, right? Cathode ray, he just conclude that cathode ray consists of negatively charged particles, right? Because the rays were coming from the cathode and it was going towards the anode, and we know that anode is a positive. Anode is positive, so it must be a negatively charged. That's why it is attracting towards the positive charge, right? Because positive charge attract each other, right? So cathode ray starts flowing from cathode and move towards the anode. He just conclude that these rays are not visible. These cathode rays are not visible through our naked eye, but their behavior can be observed with the help of certain kind of material, right? Their behavior, the cathode ray behavior, we can observe with the help of certain kind of material, which is fluorescent material or phosphorescent material, right? And these phosphorescent material, they glow when heated by the cathode ray. Okay. Now see what he did. J.J. Thomson, he just uh, he just did the same experiment in the presence of electrical or magnetic field, right? When he apply the electrical field, see, when he apply Just showing it over here. Yeah, see over here. See here, Sanndidhi. So when he applied this electrical field, right, what he observed with the in the absence of electrical or magnetic field, the cathode ray was traveling in the straight line, right? It was in the straight line. But when J.J. Thomson applied electrical field, what he observed that this cathode ray deviates from its path, right? It deviates from its path. Here you can see the deviation, right? The straight line में ये जा रहा था, by making some angle, it just deviate, right? Because cathode ray is negatively charged, so in the electrical field, it deviates towards the positive charge terminal, right? Negatively charged था, ये positive charge terminal की तरफ ये deviate कर गया by making some angle. Okay, Sanidhi?
Yes, ma'am.
Okay, so he observed that in the presence of electrical field, the path of cathode ray deviates, right? It makes some there he observed some deflections. Okay, deflection he just observed. Similarly, in the case of when he applied the magnetic field, what he did just when he applied the magnetic field, for example, see over here. Hmm. What he observed when he applies some magnetic field over here, what he observed, the path, this cathode ray deflect towards this magnet, towards the magnetic field. Okay, so he just concluded that in the absence of electrical or magnetic field, the cathode ray travel in a straight line, right? But if he apply the electrical and magnetic field, the cathode ray it shows some deflection. Okay, deflection towards the magnetic field and towards the positive terminal of the electric field. Clear?
Yes, ma'am. Okay.
In the presence of electrical or magnetic field, the behavior of cathode ray was just similar to that of negatively charged particle, right? Because it was just attracting towards the positively charged. So the behavior of cathode ray was just like negatively charged particle, right? Because negatively charged particles attract the positive charged electrode, right? So it was just similar to that of negatively charged particles. It suggests that J.J. Thomson it suggests that cathode ray consists of negatively charged particles, which is known as electrons. Okay, which is known as electrons. So that's why electrons are negatively charged particles. Fifth was that the characteristics of this cathode ray does not depend upon the material of the electrodes, right? It doesn't depend on the metals you use as an electrode, and it doesn't depend on the nature of gas which is present in the cathode ray discharge tube. Okay, so it doesn't depend on that. So we can conclude that electrons are the basic constituent of all the atoms. Okay, so that's the experiment which was performed by, yes, Sanidhi, do you have any doubt?
No, ma'am.
Okay, so this was the experiment which was performed by cathode ray experiment, which led to the discovery of electron. Now you can write down.
Ma'am, with the diagram?
No, you can draw the diagram after the class.
Okay, ma'am.
Simply, you can just draw the rough diagram.
Okay. Can you please scroll down?
Yeah, Sanidhi, in the cathode ray discharge tube, basically, J.J. Thomson used the hydrogen gas, right? And most of the scientists basically used hydrogen as a standard gas. Why? Because of lightest weight, right? Hydrogen gas is lighter in weight.
Okay.
That's why hydrogen is often preferred, right, due to its simple atomic structure, you can say, or hydrogen due to its ease of ionization, right?
Okay. Yes, ma'am, done.
And let's see the properties of cathode ray. What are the properties of cathode ray? So see, what about first is cathode ray travel in a straight line, right? In the absence of electrical and magnetic field. Right? And cathode ray produce mechanical effect, right? Cathode ray produces mechanical effect. J.J. Thomson, when he put a wheel in the path of this cathode ray, he observed that the wheel starts to rotate, right? So what does this mean? It means that cathode ray produces mechanical effect also, right? It makes the wheel rotate. Third property was that cathode ray consists of a negatively charged particle, which is known as electrons, right? And yeah, cathode ray travel with a high speed, right? And the speed is just similar to that of speed of light. Okay, so that much speed is of cathode ray. Cathode ray travels with a very high speed. Cathode ray cause fluorescence. As we have seen in the experiment, cathode ray cause some fluorescence. Cathode ray heat the object on which they fall. Why? Due to the transfer of kinetic energy. Right. When J.J. Thomson when J.J. Thomson put some object right on the path of the cathode ray, this cathode ray transfer the kinetic energy to the object, making it heat. Right. That makes the object heat. Seventh point is that when cathode ray fall on solid, right? When this cathode ray falls on solid, it produces X-rays, right? X-rays are produced. Cathode ray also possesses ionizing power, right? Means it ionizes the gas, the whatever gas is taken in the cathode ray discharge tube, it ionizes that gas through which they pass. Okay, it has a
Yes,
ionizing power. Yeah, cathode ray can penetrate through thin metallic sheets also. It can penetrate that thin metallic sheets. Cathode ray doesn't depend on the nature of gas taken and the nature of electrodes, which was taken in a discharge tube. So that's the properties of cathode ray. You can take the screenshot also. After the class, you can write.
yes, ma'am.
Done?
Yes.
Okay, now see the determination of charge to mass ratio. Right. So we know that electron is a low mass. Electron has low mass and it is a negatively charged particle. Right. So it can easily swing by passing close to other electrons. When the other electron are passed passed close to that electron, so it will make swing. Right. That electron will swing. Right. So with the help of variation, what he did, J.J. Thomson, he performed the experiment. Uh, he just by the variation of electrical and magnetic field, he determined the charge to mass ratio. Right? What is charge to mass ratio? E upon m ratio. Somehow because we know that in the absence of electrical and magnetic field, cathode ray travels in a straight line, right? But somehow he managed by doing some variation in the electrical or magnetic field strength. He just managed to that the cathode ray will travel in a straight line in the presence of its electrical and magnetic field, right? With the help of some variation in electrical and magnetic field. Okay, and by this he observed, he just determined the ratio. Determine the Charge to mass ratio, E upon M ratio. E is charge and M is mass. Okay.
Yes, ma'am.
And according to J.J. Thomson, the amount of deviation of particle from their path is in presence of electrical and magnetic field depends on some factors. Right? Amount of deviation means how much deviation from its path will occur. Right? How much will the particle will deviate. And when I say particle, what does this mean? Particle, gas particles, right? Gas particles, or you can say cathode ray particle, cathode ray particles. So cathode ray particles, how much it deviates from its path, it will depends on certain factors, right? Now see, what are those factors? So first factor is that magnitude of the charge on that particle, means how much charge is on that particle. If the magnitude of charge is more, then the deflection will be more, right? Then the deflection will be
Can you
more.
please repeat that point again? You got disconnected.
Okay, Sanidhi, I just said that. J.J. Thomson, he said that the deviation of cathode ray particle from its path in the presence of electrical and magnetic field depends on certain factors, right? Means how much the particle will deviate from its path, it depends on certain factors. First factor is that it depends on the magnitude of charge, right? Means the particle have how much charge on it. If the particle has greater charge, means a larger charge, right? Then the larger will be deflection, right? Means the magnitude of charge is directly proportional to the deflection. Okay, magnitude of charge on that particle is directly proportional to the deflection. If the charge, magnitude of charge on that particle is greater, right, then greater is the interaction between electrical and magnetic field, and greater will be the deflection, right? So it depends on the magnitude of charge in a positive, in a directly proportional way. First point is clear or not? Clear?
Yes, ma'am, it's clear.
Yeah. Second point is that it depends on the mass of particle, right? The deviation of particle depends on the mass of particle, and the mass of particle is inversely proportional to deflection. If mass is more, if larger heavy particle is there, then the deflection will be less. Okay, and if the particle is lighter, then the deflection is more, greater will be deflection, and vice versa. Clear? Second point.
Yes, ma'am.
Hmm. Third point was that the deflection of electron from their path increases with the increase in voltage, right? If the voltage which is applied in the discharge tube is more, if more voltage is applied, high voltage is applied, then the deflection will be more. Okay, then the deflection will be more. And it also depends on the strength of magnetic field. If the strength of magnetic field is more, then the deflection of electron is increases. Here, the
Yeah.
deflection of electron increases with the increase in voltage across the electrode and the strength of magnetic field.
Okay.
Okay, by this, he just drawn E upon M ratio. What is E upon M ratio? So charge upon mass ratio is 1.758820 into 10 to the power 11 coulomb per kg. Right. So this value you have to remember that. Okay, this is charge to mass ratio of electron. Charge to mass ratio of electron. 1.758820 into 10 to the power 11 coulomb per kg. Charge SI unit is coulomb, right? And mass is kg, so it's coulomb per
Yes.
kg.
Okay.
Now see the charge on the electron. So R.S. Mulliken, he was another scientist. He derived a method which is known as oil drop experiment. We will not we will not discuss this experiment in details. It is there in your NCRT in the box part, right? Just go through it. Okay, after the class, just go through it. That experiment, what was that? How he performed that? It is not very much important. That's why we are not discussing it. Okay, you just have to remember that R.S. Mulliken, he derived a method which is known as wall drop experiment. to determine the charge on the electron. He determined the charge on the electron, right? J.J. Thomson determined the charge to mass ratio only, right? But he, R.S. Mulliken, he derived the charge on electron. And what is the charge on electron? Charge on electron is minus 1.6 into 10 to the power 9 minus 19 coulomb. Okay, minus
Okay.
1.6022 into 10 to the power minus 19. From this, mass of electron will be, mass of electron is charge upon mass ratio, right? What is charge here? Charge is minus 1.60, just substitute this. And we know that mass can never be negative, right? Mass is negative nahi hoga to, so we will not take this negative sign here, right? So 1.6 into 10 to the power minus 19 coulomb divided by, what was the charge to mass ratio? So J.J. Thomson derived the charge to mass ratio as 1.75, this one. So when you substitute this value, when you divide this, you will get 9.1094 into 10 to the power minus 31 kg. And this is the mass of electron. Okay, this is the mass of electron and this is the charge on electron.
Okay, ma'am.
Hmm. Clear? So have you take the screenshot?
Ma'am, 1 second.
Just take this, and after that we will see the anode ray experiment.
Yes, ma'am.
Okay, let's see the anode ray experiment. Okay, so what was anode ray? Anode ray, it is simply a discovery of proton. Right? Anode ray experiment was the discovery of electron. By this experiment, proton was discovered, right? And Goldstein in 1800, E. Goldstein, named scientist, in 1886 discovered this proton, right? And proton is also known as canal rays and anode rays. Remember that canal rays and anode rays is also known as proton. Okay, anode ray were observed by E. Goldstein but was named by Rutherford. Just remember that, right? Observe किसने किया था? E. Goldstein, but name was given by Rutherford, right? Ernst Rutherford, right? Now see, Goldstein just done the same experiment as just like cathode ray experiment. He just performed the same experiment, but in this experiment, instead of anode perforation, he perforated cathode. Okay, to see whether there is another ray also or not, right? Just to check there is another ray which is opposite, which came opposite direction to that of cathode ray, right? So let's see what was that experiment. Let's see what was that experiment. So here's the setup. Okay, so it's a canal ray experiment. It is also known as canal ray experiment. Okay, and it was performed by German scientist, which was known as Goldstein. Okay, so what he did, he just take the discharge tube. Right, he take the discharge tube. Right, and here this was cathode. Right, this was cathode electrode, and this was anode. But in this experiment, he just perforated cathode. He just perforated cathode. And behind the cathode, he just coated the wall of the glass wall by zinc sulfide material, right? Which is, you know very well, which is a phosphorescent material, which is a phosphorescence material, right? So what happened when he apply a high voltage? When he apply high voltage, what he observed? He observed that there are certain rays which are coming from the anode, and it was going towards this cathode. Right? It was going towards the cathode, and when he just passed this passes an electrode, sorry, an perforated cathode, it strikes the zinc sulfide coating, right? When it strikes the zinc sulfide coating, a bright spot is observed, right? Bright spot is developed over there on the coating, right? So the experiment was same. The experiment was same as that of cathode ray experiment, but instead of anode perforation, he just perforated cathode. Okay, and he observed that there is another rays are coming, which is coming from the anode towards the cathode in this case. Okay, and yeah, one more thing, these rays were not coming from this anode. These were coming between this anode and cathode. These were coming from anywhere from the cathode and this anode. It was not coming from this anode electrode, right? Electrode से नहीं आ रहा था. It was coming between the spaces which is there in the anode and cathode. Okay, so
Okay, ma'am.
that was the whole experiment which was performed by the anal Goldstein. Now see, what are the properties of anode rays? So similar, anode ray travel in a straight line, right? And yeah, rays are positively charged. Why it is positively charged? Because it is going towards a negatively charged electrode, right? So it attracts the negatively charged particles. So it is a positively charged positively charged particle, you can see. Yeah, anode ray are material particle. Yeah, there's a difference between anode ray and cathode ray. Just remember, cathode ray was not depending on the nature of gas, right? But anode ray depends on the material, right? Depends on the nature of gas and the material of electrode. Okay.
Yes.
E upon m charge to mass ratio of particle depends is found to depend on the gas from which these originate, right? And yeah, these were originating, these rays, these canal rays, or you can say anode rays, are uh, originating from the gas, right? The gas which he used in this is hydrogen gas. So this was originating from the hydrogen gas, right? When the rays strike on the hydrogen, it ionizes, right? And from this ionizing, because we know that hydrogen has a best ionizing power, so it just ionizes, and from that, these rays are coming. These rays are originating, right? So these rays are not originating from the this anode, this electrode. These were originating from the gas which is taken in the discharge tube, right? Which is hydrogen gas. Okay, so charge to mass ratio of particles depends on the gas from which it is originated. Okay, so it will depends on the hydrogen gas in this case. And the behavior of these particles in the magnetic or electric field is opposite to that observed for electron and cathode ray, right? Whatever we have observed in the cathode ray experiment, when J.J. Thomson applied the magnetic or electric field, it in this case it just show opposite, right? Goldstein observed the opposite behavior when he apply electrical and magnetic field. Okay, so he just conclude that an anode ray are positively charged particle. Okay,
Yes, ma'am.
proton. So what is proton? Proton is the smallest, lightest positive ion which was obtained from hydrogen. Right? It was obtained from hydrogen and it was called as proton. What is the mass on proton? Mass of proton is 1.67 into 10 to the power 27 kg. Charge on proton is plus 1.6 into 10 to the power minus 19 coulomb. Okay. Just write it down or you can take a screenshot also.
Ma'am, I took screenshot. You can scroll.
Okay. Okay, now let's see how the neutron discovered. Now till now, neutron and electron and proton are discovered, right? Now we will see how the neutrons are discovered. One second. Hmm. Okay, so this neutron was discovered by James Chadwick, right? In which year? In 1932, right? So in 1932, Sanidhi, Chadwick bombarded beryllium, right? He bombarded beryllium element with the stream of alpha particles, right? He just bombarded alpha particles on this beryllium atom, right? And what is alpha particles? Particle is nothing. It is a helium atom, helium, hydrogen, helium 2 and 4. Atomic number is 2. Here in the subscript, we will just write the atomic number, and on the superscript, we write the mass number. Okay, don't be confused in that. So, when James Chadwick bombarded beryllium with a stream of alpha particles, he noticed that penetrating radiations were produced. Some radiations were produced, and these radiations were not affected by magnetic and electric field, right? What he did, I'm
Yes.
just repeating, I'm just repeating. James Chadwick, he bombarded beryllium. Beryllium पे उन्होंने bombard किया with the alpha particles, right? When he just bombarded alpha particles, he observed that some radiations are coming. Some radiations are coming. And when he apply electrical and magnetic field, then it is not affected by that. It is not affected by electrical and or magnetic field. Magnetic field. So what does this mean? What does this mean? Because if it contains some charge, if neutron will have some charge, then it will surely affected by the electrical or magnetic field. It shows some deflection, right? It will show some deflection. But the radiations are coming, right? Radiations are coming, but they are not affected by electrical or magnetic field, right? So what does this mean? It means that there is some particles which is not deflected, which is chargeless, right? It don't have any charge, right? It means that J.J. Thomson observed that there are some radiation when he bombarded alpha particles, beryllium with alpha particles. He observed that some radiations are coming, right? Some radiation because some chemical reactions will happen, right? Some chemical reaction when beryllium his atomic number is 4, atomic mass is 9, right? And helium, which is alpha particles 2 and 4. So when he bombarded helium atom, which is alpha particles, on the beryllium atom, he observed that some radiations are coming, right? But these radiations are not affected by electrical or magnetic field. It means that there is some subatomic particles. There is something which is chargeless, which is chargeless, राइट अगर उस पे कोई चार्ज
Yes.
होता राइट अगर अगर न्यूट्रॉन पे कोई चार्ज होता तो इट श्योरली बी अफेक्टेड बाय द इलेक्ट्रिकल और मैग्नेटिक फील्ड राइट इट मस्ट शो सम डिफ्लेक्शन ओवर देयर बट देयर इज nothing like that. It doesn't show any deflection, right? So he concluded that there is some particle which is neutral, right, which is chargeless. So he just gave the name as a neutron. He just gave it a name, neutron, right? Because it is a neutral. It doesn't have any charge. Okay. Now see what he did. Beryllium is 4, atomic number is 4, atomic mass is 9. Helium is 2 and atomic mass is 4, right? So when the chemical reaction between these two happen, so it must give 4 plus 2. 4 is atomic number, 4 plus 2, it will give you 6, right? And carbon, what is the atomic mass of carbon? कार्बन का 12 होता है राइट 12 so from here you can see 9 plus 4 9 beryllium is 9 mass number is 9 and helium is 4 so it must give 13 यहाँ पे mass number 13 आने चाहिए right but here 12 mass number came he observed that there is something because one loss हो रहा है mass, one mass is lost, one lose हो रहा है mass. So where it is going, right? So where it is going because we know that according to the law of conservation of mass, mass can neither be created nor be destroyed. So it can't be destroyed. Mass can't be destroyed. So where it is going? So there is something which has mass, but it is chargeless, right? It is chargeless because it is not affected by any electrical or magnetic field. So it is charged. There is no charge, right? But it has some mass, right? One mass is there. So it just named it as a neutron. Clear, Sanidhi, or not? Any doubt?
No, mom.
Okay. Because one mass has been lost. Okay, one mass is losing from here. So you observe that there is something which has zero charge, which is chargeless, right? And it has some mass. It has mass. Okay. And neutron has mass, but it has chargeless. It is chargeless. No charge. Similarly, he has performed this experiment on boron also. So 5 plus 2, 7, right? And nitrogen atomic mass is 14. So, but from here, 11 plus 4, it means 15. Mass number should be 15, but it is 14, right? So where one mass is losing, one mass is one mass is losing over there. So it is of neutron. There is some particle which is also present